Hi, everyone. My name is Uzi. I'm the Chief Strategy Officer in Proteantex. And actually, I want to talk about functional safety today. Three awesome presentations that happened before me that actually kind of made the point, I would say even, to what I want to present to you today. So, if you look on the evolution of functional safety, the concept by itself, safety in general, is transitioning from detection and reaction into maybe a conceptual idea of prediction. And today, basically, the whole idea of what I want to talk about is it possible to do something like that? Because being reactive, especially in a safety mode, either requires changes in architecture, or alternatively, requires a different kind of mindset as to how we protect the actual passengers in a car. And so everyone spoke about software-defined vehicles. Yeah, actually, it's a major driver to everything that is happening right now. The idea behind it that software is driving, and the whole millions lines of codes and so on is driving or responsible for our safety inside a car is actually what's driving this whole idea of how to think about functional safety, but from a different perspective. And when we talk about that, actually it's interesting what drives software-defined architecture, right? The decoupling of software over hardware, I think you all heard about it. At the end, different companies are producing hardware, different companies are producing software. Sometimes it connects, even if it's the same company, it's spread across different teams. And we'll talk about that in a second, kind of what that implies. There's also different development methodologies. If you compare how software is being done with agile mindset behind it and transition to agile development methodologies, then the idea of that versus how hardware is produced is completely different. And then comes into mind different business models that comes into play. So there was an idea about the fact that new features will come, new software updates. Maybe there would be like an iPhone on wheels, basically, that would allow you to buy and feature and license stuff. But that's not the only thing that can happen. And maybe as I start my presentation, before going into this concept of the architecture, which is really the point of what I want to kind of emphasize today, I do want to talk a bit about business models. So, probably most of you read a couple of weeks ago about the fact that now GM and Ford were going to use Tesla's charging infrastructure, right? It's not, it was kind of everywhere. But on that same week, there was a tweet from Elon Musk saying, we will be also happy to license the FSD technology to other car manufacturers as well. So it came to my mind when he says that, and this is crazy company by itself, so the innovation there is awesome. It won't be surprising if that's something that could happen. Actually, if you would have thought about using the charging infrastructure for Tesla, that was a science fiction probably just a few days before, but it is happening. But when you think about when he says licensing the technology, what does he mean? Like the technology itself is not just the software, it's not just the hardware. Actually, it's the heart of the car. It's connected everywhere. Not including the maintenance, the software updates, everything. So it's kind of like the analogy to the human body. Someone would start generating a heart and give it to everyone, license a new heart for the human body. And so it came to me that this whole change in architecture is really kind of in the heart of everything you've seen today, right? How many versions of this slide have you seen today? Of the transition into the centralized domain architecture, centralized domain compute, and then compute and connected. Just now, we heard about that connection. There's one aspect that is not really too much dealt with, which is what are the reliability implications of that transition, right? Because if you look, each one at the beginning was this separated, but was a single point of failure. If there's a problem there, you could have fixed it. As you move right, you are highly dependent on very advanced computers, powered probably by ARM or RISC-V or any other compute technology. But at the end, they are centralized, and even with redundancy, they are responsible for the safety of the driver that is actually going to use the car. Now, there's one thing you haven't seen today, which is maybe just in a glimpse from Deepti's presentation. I want to give you a personal perspective about this slide. On the left side, you can see our CEO, Shai Cohen, driving a VW Karmann Ghia from 1969. And on the right side, you see me quite happy with my Audi e-tron after I had like a huge mental change of actually transitioning to a full EV car, right? But if you try to compare between the two, first look at him, he's very happy. This car drives up until now very nicely. It's a beautiful car, drives perfectly, not a single compute element in this car. Still is happy. On the other hand, you see me on the right side. It's a massive machine, this Audi e-tron, from every aspect you can imagine. But fundamentally, I'll say, some will tell you that the only difference you see here in this car is the difference between on-the-ground CEO and the chief strategy officer being ambitious on the car that he's driving. But that's really kind of a major difference, just out there, the evolution in not that many years, still a few, but not that many years, in the transition between those two kinds of technologies. And now, what's powering that? You saw it throughout the entire day, right? The advancement in the technology itself, in the hardware itself, the move to chiplets, right? There's a lot of discussion about chiplets, but probably how many of you thought, how do we test this thing? Right? Today, the ability to test an SoC, which is comprised out of many chiplets that maybe come from different vendors, is at best case scenario on a pass-fail level. And then you ask yourself, was it tested really with the same software? And even if it did, because of continuous integration or because of other methodologies, how that perform over time? Because the software will get updated and use the same hardware as it moves forward. And then you heard about the advance of the process nodes. We're seeing now 5, 7 in the car, probably soon enough 3s, and maybe later on a 2. What does that imply from a reliability standpoint into actually using that kind of a technology in a running car as you use it? Now, if that's the case, where you have software-defined architecture and you have hardware advancements that are kind of even moving kind of in parallel, then you ask yourself how those guys actually communicate. So I want to say about myself. 2/3 of my career is in software engineering. I used to be a software engineer myself for many years, ran R&D teams in different capacities, from 10s to 100s. And then I want to tell you 2 shocking things about software engineers. If I would have stopped in the corridor every one of my engineers and asked him, there's a problem, like there's a bug. So the answer would be almost immediately, what's the issue? I'll patch it. Okay. Second question I'll ask him, do you care about what hardware you're running on? Have you considered that even? Like you run your code over something, you ask what is 1 + 1, you'll get a 2. What happens if you get a 0? He'll tell you, no problem. Probably there's a problem with the computer, I'll replace it. It's not really an issue. Those guys are, by the way, the same engineers you hire to do, right? Also the software-defined next generation vehicles, right? Not too many of them have grown up to be super hardware embedded engineers that knows exactly the nitty-gritty of the hardware to be able to actually write software that takes advantage of it in a way and consider all the aspects of what does actually that implies. And same about that. And what's funny about here is that you see people here which are hardware engineers talking about software, and you see software engineers talking about hardware. It's just reality, right? Because those two worlds now collide together, and that's in the actual car we're driving. And then you ask yourself, okay, so from a reliability standpoint, what does that mean? Like, over time, right? Can I really trust what I'm driving? Can I really trust on the software I wrote? Can I trust on the hardware that was manufactured for the next 15 years? As the autonomous functions don't care. They actually continue to work in the car, not really understanding if I'm on the first year, not on the first year, and so on. So the reliability aspects come into place in a very strong way, which brings me to the point that this curve, that probably many of you saw in different capacities, right, has two different sides. One side is on the left side, which you ask yourself, okay, I produced the device, I wrote the code, everything is great. How can I predict time and failure rate before this thing goes out to the field? There's defects which are very hard to identify today. Some of it is not really testable. You ask yourself on that chiplet technology, when you have interconnect, die-to-die, parallel interface which is connecting the two dies, do you really know behind the pass-fail information how long this lane would live? Can I switch it? Do I know if it's going to last forever, or do I have a problem? Maybe I have a problem with some of the lanes, not everyone, not all of them. And so on the other side of things, you see the accelerated aging, the application stress over time, new software updates, all of that stuff which is coming on the right side, which is basically causing you to think how long would really the device would live, and how can I assess it? Are there any techniques today that would help me assess what's going on in my car? The car I'm driving, the car that is responsible for my safety as a passenger. So with that, the problem is evident, right? I'm pretty much sure, between everything that was spoken today, it's quite understood. But there is also a concept about standardization. And standardization that was also, I think, articulated before by others, are actually, there's two things that is driving them. One are the OEMs themselves. I heard Johannes saying that there's now much more connection between car manufacturers and the actual semiconductor companies, and of course the tier ones in between. But the actual thought behind it is how can we improve the existing state? And not just by saying, okay, we'll work together, probably we'll do a team which is doing continuous integration and build the software and the hardware together, which is happening a lot, and then we'll ship the thing. Okay, so you shipped it, and what happens after that? How do you monitor that? How do you know it's actually continuing to perform over time as you originally shipped it? And then comes standardization. So you all heard about UCIe, most of the discussion about chiplet. There's two things I want to say about standardization, aside from the fact it takes a long time. But this concept of predictive maintenance and the fact that the whole movement to chiplets requires a different approach about how you can actually monitor devices is it's already there. Actually, on the predictive maintenance side, there is a technical report right now which is being voted, and for the next submission of the next edition of ISO 26262, there would be a topic about predictive maintenance, which I encourage you all to take a look, because I think it's kind of also towards the end of my discussion, wraps up about what I want to present to you in a second as a conceptual idea for actually a practical idea on how to do that. And the second thing is Mercedes and GSA presenting in the UCIe about the idea of in-field monitoring of lanes between different chiplets. So the idea behind it is to actually kind of bring a different approach which is driven by data, driven by AI. It wouldn't be a presentation without saying the word AI, but actually it is driven by the ability to analyze it at scale and analyze it in a way that is not really working by the book, but through machine learning models and artificial intelligence, doing that in the field, actual telemetry that comes out to assess the health and the performance of a device over time. With all the changes that is happening there, trying to combine software and hardware together. So what kind of an architecture would enable that? What kind of data would enable that? So the idea is that the SoC, actually the chip itself, whether it's a multi-chip package or a monolithic chip, would actually report the health of the performance, how it's doing with telemetry data over time. And over time, we really mean that it's an entire software stack that would actually enable you to use this data, the analysis, either in the car, on the chip, in the car, and in the cloud, in a way that would actually be useful for you to take decisions and assess how you're performing over time. And my last slide, and I'm at time, that's what we do in Proteantex. We are an innovator in the health of performance monitoring. We've innovated the idea that throughout the eyes of the chip, you can actually generate telemetry data of millions of actual logical paths inside the chip that attest for the performance of the device. Use it on the chip itself to optimize power performance, but also on the car level and later on in the fleet. And this data would be crucial, basically to do the predictive maintenance or the time to failure analysis and optimize how software and hardware are working together in an actual car. So with that, I'm done. Thank you. Thank you very much.